Yeah, so this is lecture 8 in this course on quantum computation, computational models rather. And today we'll be talking about quantum error correction. So this is not a course on quantum error correction, so we just have a little bit about that subject, but enough to appreciate the significance of it. So this is a lot of material, and I want you to help me a little bit in establishing it. So I don't know if we're actually going to make it through, but we'll give it a try. So about this whole stabilizer formalism, we've done the first part. You could call it the ugly, although it's not really ugly. It's just a clarification. That's the Goddess-Manil theorem. So quantum computation in the Clifford fragment can be efficiently classically simulated. So no speed up there. And the next thing is that quantum error correction very much relies on the stabilizer formalism and the codes that come with it. So it's actually very useful. And then there's a really stunning thing, and we get to that at the very end, maybe. Okay, so that's the outline for today. Now we talk about quantum codes, popular ones, and then how to operate on codes with gates. Okay, so why quantum error correction? Oh, sorry, these slides were in the wrong order. So again, I give you a few references for papers you may read up on. So the Nielsen and Chuang chapter 10 contains most of what you ever wanted to know about quantum error correction. So that's the primary reference. Then on special codes, we have the surface code. This is a code we introduce later, and but very briefly only, you see it later in this course. Then you see another code that is actually important for today and will be important for our first model of quantum computation. So that's the Reed-Muller code, Reed-Muller quantum code. You can read up on that in this paper here. But that paper will become more prominent in the next lecture. Good. And then, well, the real Reed-Muller codes were classical codes, and you can read up in this book from half a century ago. Good, so this is reading, and now we come to the motivation. Okay, we all know that, a quantum register of a bunch of qubits is an idealization, and it doesn't really exist in the real world. So in the real world, if you're lucky, you have a quantum register, but then you have everything else around it. So we call this an environment, and between the two you have interaction. And you can shield that to quite some extent, and well, however hard you work, you will never completely remove this interaction. So there will always be residual interaction. And you know what that does? It entangles the quantum register with the outside world. And if you only look at the quantum register, which is what you can realistically do, it will make the state of the quantum register more mixed. It will turn from pure into mixed and becomes classical. So here goes your computational power. So that's a problem. And quantum error correction is the art of performing quantum computation in the presence of all of this unwanted interaction. Yeah, and so the cornerstone result of this field is the threshold theorem. So it says that if you have a universal quantum computer, if the noise level per gate is below a constant error threshold, so it can only be so noisy, then, but you can have a finite amount of noise on it, then this is this is almost as good as no error at all. So this is, of course, an oversimplification, but you can tolerate a finite amount of decoherence per operation, and at least in the scaling sense, it will not cost you all that much. Okay, so this is the main result in this field. Okay, and we want to learn some aspects about the constructions that are behind it. Okay, making quantum codes. But before we go to that, just let's see how quantum error correction could work and how it could be different from classical error correction. So let's compare the classical bit and the quantum bit. Classical bit, just two states, 0, 1. Measurement doesn't affect the state. Set of states are discrete. Quantum bit, completely different. You have a continuous set of quantum states, even if you have just a single qubit. And measurement does affect the state. So you need to be careful about doing measurements. Okay, and so despite the differences, quantum error correction is actually possible, and it even builds on classical error correction. So you could think, and so this is a puzzle. So hopefully halfway through the lecture, you can resolve this puzzle for yourself. Okay, so here's a puzzle. On this slide, I argue that quantum error correction is not possible. And the argument is something like this. Okay, so when here, for comparison, it appears to be a different situation. So physically, in a circuit, the level 0 could be, this would be a voltage level, so this could be 0 volts, say, and this could be 5 volts. And then it's easy to detect when errors happen. So maybe you find your voltage level 4.7 or something like that, and you think, oh, that's illegal, but it's close to 5, so it's probably supposed to be 5, and you're correcting back. Okay, so that seems reasonable, but here it's different. So you have a quantum state, and you perturb it a little, you get to other quantum states, and these are all legal states. You're drifting around in your state space all the time, going through legal states. And so what do you correct for, really? Yeah, so where do you correct to? Okay, it seems like if you know you have drifted a little bit, you wouldn't know where to correct to. And so it seems no way in such a continuous setting to make error correction work. Okay, so this argument isn't quite right. And I hope by the end of this lecture, you know you can argue against it. Can you argue against that right now? Do you know why this picture is not adequate? What I just tried to suggest over here. Okay, no, that's good then. Okay, so hopefully later you will. Okay, so now let's finally get to making quantum codes. And so we begin with a classical code, and it's called the repetition code. So you have two logical states, logical 0, logical 1, and the coding is just to repeat the state 3 times. So this is the encoded 0, this is the encoded 1. Yeah, just very simple classical code. And now, you can use this for error correction. So you'd think maybe errors happen independently on these bits. So if you find that, well, then it's more likely that this bit was flipped than this and that bit were flipped. So if you see this, you think, oh, it's supposed to be that. Likewise, if you see this, you think, oh, it must be that, because you get from here to here just by one flip. Okay, so the way this procedure runs is you individually read out all bits and perform a majority vote. Yeah, very simple idea. Okay, there's a problem here, though, if you want to generalize this to quantum, and that is, in the process of doing the error correction, you learn the encoded state. And quantum mechanically, you probably don't want that because you want to preserve linear combinations. Superpositions. Okay, so that majority voting idea is not going to work in quantum. But there is now an equivalent way of dealing with this repetition code. And we'll see that that can be generalized to quantum, and in fact, you already know the generalization. But let's not get ahead of ourselves. So what we can also do, rather than measuring everything and do a majority vote, is to compute a syndrome. Okay, so you take your affected code word, like so, and multiply it with a matrix, this one in this case, and what does this matrix do? Again, this is all addition modulo 2. So what this matrix does, it compares this value to that value. Supposed to be the same. So if that doesn't happen, like here, then it reports a flag for an error. Yeah, and here the same. Those two bits are supposed to be the same. If this doesn't happen, yeah, you get a bit of syndrome. Okay, so you compute some extracted message from which you want to identify what the error was. So the interesting thing is that this parity check matrix, when you apply it to a valid code word, yeah, the syndrome is going to be 0. And furthermore, this is a linear operation. And so if you have a code word plus an error happening on it, then this is a function of the error only, not of the code word. Yeah? It's a function. So when you do that syndrome thing, you learn the error and nothing else. So this is exactly what we want. Yeah? So we do not want to learn anything about the encoded state because that would destroy it. And so this seems to be a starting point for making it quantum. I mean, it's still classical, these parity checks, but that kind of looks right. And yeah, and so this is now how you do that conversion from classical to quantum. So first we take this repetition code, classical repetition code, and make it a quantum code. Yeah, so we just allow superpositions of these states. So this is 1 qubit now encoded in 3. That would be a quantum code of sorts. We'll discuss it later, how good a quantum code it is. Okay, so but now the essential thing. So the clever thing was a parity check matrix. Now you want to convert the parity check matrix into something quantum. And that's what it is. First row of the parity check matrix becomes this tensor product of operators, Z1 tensor Z2. Second row of the parity check matrix is becoming Z2 times Z3. Sorry for the typo. Yeah, okay. So it's really rather, so the second element here is Z2 tensor Z3. Okay, and these look familiar. I mean, they look like stabilizers, Pauli operators that pairwise commute. Okay, and well, there's only 2 of them, maybe for, and they are linearly independent, but maybe you were expecting 3, now it's only 2. And there's a reason for that. Namely, they have to stabilize a space, not just a single state, but they have to stabilize both code words and all the linear combinations of it, which they do. You take any such state here, apply such an operator, it is an eigenstate with eigenvalue 1. Likewise for this operator here. And so that's the idea. This is the quantum counterpart of applying a check matrix. You measure these operators. You expect to find eigenvalue plus 1, and if you don't, then you know that an error has happened, and you want to find out from this pattern of eigenvalues what the most likely error was. Yeah, okay, stabilizer group is by now a familiar concept. It's just a smaller group because we want to stabilize a non-trivial state space, namely C2. So it is a little bit of something for you to do now. So yeah, so show that these 2 operators do indeed generate the code stabilizer. So that means you have to show that they are both stabilizers, and then you want to show that there's nothing else. Okay, so then there's a bunch of other operators here. Maybe you find out what they could mean, and then look what this Pauli operator Z1 does on that code space, and maybe it puzzles you, maybe it doesn't. So we'll discuss this in 5 minutes. So please take a bit of time and think about these questions. Okay, so do we have any ideas about any of these questions? Anybody wants to say something? Okay, so let's see. Good. So let's just kind of talk about it briefly. So yeah, so it's easy to check that these 2 operators do stabilize the space pointwise. So every state is stabilized by them. And so then you will see that you find nothing else that does the same. So there's other operators such as these down here. They stabilize the space too, but not element-wise. So they will take, so for example, this guy will take this portion of the state here to the encoded 1 and this portion to the encoded 0. Yeah? So it basically exchanging alpha and beta. So you stay within the space, but you're mapped to another state. Yeah? And so for the Z, it is the same. Yeah, okay, and so that brings us to the significance of these operators. So what is the significance of these operators?
One question.
Yeah.
Okay. Is there any way to easily see that this is the case, that there are no other operators that do this element-wise? Or do we just have to multiply the general state out and check all the conditions?
Yeah, I mean, informally speaking, maybe you can formalize it for yourself. So whenever you impose such a constraint, you're cutting the Hilbert space dimension in half. Yeah, so there's this operator, I mean, acting on 3 qubits, it has 4 eigenvalues plus 1 and 4 eigenvalues minus 1. Okay, and so you're enforcing it as a stabilizer. So the minus 1 half space, I mean, space is eliminated, so you're going from 8 to 4, and then you enforce on this remaining Hilbert space a second condition. You go from 4 to 2, and yeah, and so any other, so that's what those two operators do. They get you from Hilbert space dimension 8 to Hilbert space dimension 2, which is where you wanted to be. Yeah, you wanted to encode 1 qubit. And if you enforce another such operator, if it is independent from those two, it will cut the dimension again. And that's not what you want. You want to keep that Hilbert space. Good. Further questions? Yes?
Would Z1, Z2, and Z1 and Z3 also work?
Yes, it would also work. And the reason is that Z1, Z3 is the product of those two. Yeah, and the stabilizer is always a group. Okay, then let's think about these operators. What do they do? I mean, it's basically just what I talked about half a minute ago. Okay, so what they do is they are not as, I mean, they have a different purpose than these. So these operators, they do stabilize the space, but not element-wise. Yeah, so they map states in the space to other states. So this triple X exchanges this portion of the state with that, which is the encoded 0, which is the encoded 1. So this is the encoded X operator. This guy, let's see what it does. It leaves this state alone. This portion, the encoded 1, gets a minus sign, a minus sign, a minus sign. 3 minus signs is a minus sign overall. So encoded 0 goes into itself, encoded 1 goes into minus itself. And so this operator is the encoded Z. Good, so you have the stabilizer and you have your encoded Pauli operators. Okay, so which is something that you might want. If you compute on the encoded level, you want to know what your encoded Pauli operators are. Okay, but now let's look at this guy. Z1, what does it do? Yes?
Same.
Same. Yeah, exactly the same. On the code space, this guy does the same as this. Does this concern you in any way?
In this case, we cannot distinguish between the application of one Z operator acting on one single bit of the qubit and 3.
Yes.
Simultaneously, so we make no difference afterwards.
Yeah.
So if some phase is flipping for one state, it's the same as phase flip for the whole state.
Yes. That's it. And the question is, does that worry us? Okay, so maybe I wasn't clear. I did say this, maybe I didn't emphasize it enough earlier. So we said, when we discussed, maybe I should have emphasized this. Okay, so we have the errors. Yeah, so remember we assume, and it's kind of physical almost, that our errors are dominantly local. And so classically, you have a bit flip. Now, quantum mechanically, you have a bit flip too. So the Pauli operator X is the quantum counterpart of our bit flip, but then you have the phase flip too, a local phase flip, and the combination, which is a Pauli Y. Okay, sorry, I think I didn't emphasize this. So these are the errors that can occur. And so now the problem is that this guy is simultaneously a gate, an encoded gate, and a likely error. That's not good, yeah? So there is an error that occurs very likely in leading order that does an encoded gate. So our code does not protect us from this. So we will never, when such such an operation occurs as an error, we will never find out. And that means that this code that we are just looking at, this repetition code, is not a good quantum code. It's actually a super bad quantum code. This code is worse than not coding at all. But it's good as a pedagogical tool. Yeah? So we only look at it for pedagogical reasons. It's not recommended as an actual quantum code to use because it's unstable towards phase flips. Okay, more checkup. What do we really need to do? Let me think. Okay, so can you help me? Let's go through the first items here. So we know that here's our pedagogical code back, and we know that's super bad for phase flips. So let's assume phase flips don't occur, so that we can still work with this code a little longer and see what it tells us. So let's assume X flips is the only thing that occurs. Yeah, so we have every one of these Pauli operators X is applied with a certain probability P, and that's what's happening here. And so we want to know how this code performs against such a noise. Okay, this is just only a pedagogical exercise for now. We will find better codes later. Okay, so now can you answer question A? Yes.
P times 1 minus P squared.
Exactly. Yeah. So everybody, I hope, understands that. So the error on the first qubit is P, and then the error on the second qubit not occurring is 1 minus P, and on the third qubit, error not occurring is 1 minus P. And these are independent events, so you just multiply the corresponding probabilities. So it is, as you say, P times 1 minus P squared. Okay, and and so is there okay, so what is the error syndrome for that error? If you remember, so our stabilizer operators were this one and that one. Oh, maybe I should explain something that since this is just a super brief review, that I didn't say. So let's suppose we have a Pauli operator, whatever it is, x1, let's just call it an error, applied to an encoded state, psi bar. And then we measure a stabilizer operator, G. We want to know what the eigenvalue is with respect to this operator. Okay, so you can easily compute that. And so it only depends on whether our stabilizer element and this error commute or anti-commute. Yeah? So we exchange the order of the two, so this gives us -1 to the commutator the way we wrote it yesterday. Okay, and then the stabilizer and the error in the exchanged order apply to our encoded quantum state. And so since it is a stabilizer, yeah, so just it becomes that, and now we see we have the same error-affected state on both sides. So we have an eigenvalue equation again, and so the eigenvalue corresponding to that stabilizer will be +1 if the stabilizer commutes with the error, and it will be -1 if the stabilizer anti-commutes with the error. So it's just about commutation or anti-commutation of Pauli operators. Okay, so it doesn't really depend on what the encoded state is or anything. It just depends on the commutation or anti-commutation between the error and the stabilizer. So with this, tell me what the syndrome is for this error x1. Oh, what is meant by syndrome? It is the eigenvalue of the stabilizer operators when you measure them. -1 for one. For which one? So we have two. We have this and that.
For x1 for z1, z2.
First one is Z1, Z2, yes. So what is it?
Should be -1.
Should be -1 because the anti-commutes with x1. And for the other?
1.
1, yeah, because it commutes. You see, these operators have different support. And now if you try it with another error, so for x1, let's write it down. For x1, you have the eigenvalues -1, -1. So if you do the same game, say for x2, yeah, it's just a matter of commutation, anti-commutation. You anti-commute here and you anti-commute here. And so it's going to be, oh, excuse me, it was a +1 here, I apologize. Yeah, so for this operator you have commutation, so it's a +1. Okay, so now for x2 it's -1, -1 in fact. So you see these two errors, they have different signatures. And for x3 it's another, so let's do that too for good measure. It's another signature again. So you have commutation here, but anti-commutation here. So it would be +1, -1. So you see all the 3 1-qubit errors that you have, which are the dominant ones, they can be told apart. And they can further be told apart from the identity, which is even more likely, yeah, because identity has +1, +1. Okay, so you can tell them apart, which is good, so you can correct them. But then there's maybe more errors that can happen. You can also have correlated errors. So tell me, and this is now part C, what error, if any, has the same syndrome as x1?
I assume it's trying to lead somehow to many bit errors.
Yeah, you are allowed to venture into many bit errors because the 1-bit errors or 1-qubit errors we have already looked at. So
x1, x3.
x1, x3? Okay, let's see. x1, x3. Let's write this down. x1, x3. So here we have anti-commutation. And here we have anti-commutation too. Yeah, 2, 3. So this gives us -1, -1, which is the same as x2. Okay, good. What was not, but now maybe you see a pattern now. Maybe the next guess, yes?
Yeah, x2, x3.
x2, x3. Yeah, so x2, x3 is right. So let's just check that, and you know why, because it's the complement of x1. Yeah, so x2, x3. So we have anti-commutation here and commutation here. So it is -1, +1, and that's hopefully the same as the syndrome of x1. Yes, it is. Okay, good. Okay, so these two errors have the same syndrome. So the error correction procedure doesn't tell them apart. So when that syndrome occurs here, you don't know what happened. It could have been this error or could have been that error. So what do? You want to correct your error. Which one do you pick?
Most probable.
Most probable, exactly. You pick the most probable, and then if that occurred, then you did the wrong thing. So then you occur an error and you'll never know. Okay, but this is an order p² event. This is an order p event. So that's the most likely, that's what you correct for. And if it was that, you make that error. Or to be precise, it's p² times 1 minus p. Okay, so this is how the error correction procedure fails. It can fail, and we deal with that later. For now, we just observe, okay, we have corrected for the dominant errors. Yeah, and we will continue with that in a moment. And so let's just summarize what we have found so far in this example. So we have generalized the idea of stabilizer states to stabilizer codes. Yeah, so you have again a stabilizer group that stabilize now not only an individual state, but rather a state in a code space. So it's any state in that code space, it's now a subspace of the Hilbert space. The error correction works by repeated measurement of these stabilizer operators, yeah? So we just found in this example, and this is in general true, that these eigenvalues that we measure, they tell us whether errors have happened or not, and if errors have happened, what these errors were. And so then correctable errors anti-commute with at least one stabilizer operator, so this is the error syndrome. So they make themselves known. Yeah, and then from what the syndrome is, you can identify the error, however, with some limits. We saw that too. Okay, and so it's all about commutation or anti-commutation, so that's what we did here on the board. Yeah, it's not about the encoded state, and it couldn't be, because when you do the error correction, you're not supposed to learn what the encoded state is. It's only about the error and how it commutes or anti-commutes with the syndrome operators, or with the code stabilizer operators. So that part, the syndrome informs about the error, but not about the encoded state. Good. Okay, so that's a summary. But we have this problem that we have only suppressed the error, not eliminated it, and that's something we will have to get back to. Good. Okay, so this is maybe a formalization of the situation. So our physical insight that we gain from this example is that we cannot correct for all errors. Our error correction routine will sometimes make mistakes, and we'll have to deal with that. So and kind of on a formal level, how we deal with the situation is we split up the set of errors that can occur. We define a set of correctable errors. That's hopefully the most likely errors, and in our example here, it was the 3 local errors could be corrected. So we define the most likely errors, and then we have a condition for when the most likely errors are correctable, and I'll explain it in a moment. And then we have all the other errors that can also occur, and we require of all these remaining errors that we cannot correct, that they are unlikely. Okay, and we want to make them arbitrarily unlikely, and we'll talk about that. So now let me explain the error correction condition. So what we need to do is that, so it's not about individual errors, but it is about pairs of errors. So what we want to do in the error correction is we want to be able to tell errors apart from one another. Yeah? So one error can occur, another can also occur, and we want to be able to distinguish them. Okay, so here are the 2 errors that can occur. So they can be distinguished by their syndrome, that is, they have a different syndrome if this condition holds. Yeah? Remember, the syndrome information is about commutation and anti-commutation, and if there is a Pauli operator, a stabilizer operator that anti-commutes with the product of them, this must mean that the first error and the second error, they behave differently under commutation with that syndrome operator. So one commutes and the other anti-commutes. So that gives you the overall minus sign. So they behave differently under measurement of that syndrome, and that means I can tell these errors apart. But there is another possibility. So if they cannot be told apart, this is not the end of the world. There is another thing that can happen. And it's possible that even though they are different operations, they can have the same effect on the code space. Yeah? So so for example, Z1 and Z2. So Z1 we saw was an encoded gate. The code is permutation invariant, so Z2 does the exact same thing. So Z1 times Z2, commutes with all the stabilizers, so the stabilizer cannot tell them apart, but it doesn't really matter because the product of these operations is a stabilizer, and so this means the operations do the exact same on the code space. So we cannot tell them apart, and also we don't have to. So this is the two things. Either we can tell the two errors apart, that's good, or we can't, but it doesn't matter. Yeah? So these are the two parts of the error correction condition. If all pairs of errors either satisfy this or that, then we have a correctable set. Okay, so what we have seen so far is a situation like this. So what is plotted here is the physical error probability for the local errors and the logical error after correction. So we've seen that sometimes the error correction procedure fails, but this is a quadratic effect. So what we have done so far, and it's not going to be enough, but we'll deal with it, is a suppression of error. So previously, I mean, the error probability was p. Now it is something that starts with p squared. And if the error probability p is already small, squaring it will make it smaller. So this means for small error probabilities to begin with, our correction procedure has made things better. If you increased, that's the main point, it has made things better. Okay, but now you ramp up the error probability and you'll find there is an intersection point, and if you are beyond the intersection, then error correction actually makes it worse. Good, but main point is, if the error probability is small enough to begin with, you make it smaller, and how small is small enough? So what we want to do now is, and that's after the break, we want to make this curve very, very steep, essentially a step function. So we want to find codes so that the error is arbitrarily suppressed until you hit a critical error probability value, and then it jumps up. Yeah, okay, so from this mild suppression to very strong suppression that we still have to do, and we do this after the break. So the remaining point is to make this very steep, something like this. Okay, and we want to talk about how, and then we have a bunch of other points to discuss. But let's do one step after the other. The code that we so far looked at, this repetition code, the quantum version of the repetition code, it was not a good code. So we haven't even a single code yet. So that's the first thing we have to fix. We need at least one good code, or one decent code, proper quantum code. And a proper quantum code is one that corrects all one local errors. Yeah? So these in a local error model are the leading ones. Yeah? Spin flip, phase flip combination for all of the qubits present. Yeah, so at least those need to be corrected. If we can achieve that, then we have suppressed the error from order p to order p squared. So that's good. And we'll see later how to make it better, but that's a start. Okay, so there's a 7-qubit code, a so-called Steen code, that does that. Yeah, let me show you what this is. And here you have it. So I have done this in a bit of a graphical fashion. So depending on whether you are 2-dimensional or 3-dimensional, you either see a wheel here or a cube with one vertex missing. Yeah, doesn't matter either way. Okay, so here is what the stabilizer operators are. So there's 6 of them, and that's actually good. So remember that dividing Hilbert space dimension argument I gave to you earlier. So we have a Hilbert space dimension of 2 to the 7 for 7 qubits. And so we divide by 2, 1, 2, 3, 4, 5, 6 times. So 2 to the 7 divided by 2 to the 6 is 2. That's the remaining Hilbert space dimension. So we have one encoded qubit. And you see the encoded Pauli operators for that one qubit here. So this is the encoded X, and this is the encoded Z. So you have the encoded X is the tensor, 7-fold tensor product of individual X's, and the same for the Z. And you can check the computation relations. Pauli operators X and Z are supposed to anti-commute, and they do because it's an odd number of minus signs. Good, so that checks out And the stabilizer generators look like this. I mean, there is a pattern here. Maybe, I mean, it's kind of symmetric. And yeah, we don't need the mathematical description of these shapes here, but it's reasonably intuitive, I think. So that is our stabilizer generators. And so these 6 operators you would be measuring for that code to correct errors. And so, okay, just a reminder where we want to go to. We want to, I mean, we can't do it in this lecture today, but ideally we wanted to go to establish the threshold theorem. Well, today we are looking at something much simpler, at least so far. Yeah, I see your hand, just in a moment. For now, we are not operating on quantum information with gates. We are only, for so far only looking at memory. So we're just trying to keep an encoded quantum state in our quantum memory coherent and unaffected by errors. And yeah, we deal with all the rest later. And so we want to go from here, this quadratic suppression, to arbitrary strong suppression of error. And we'll do this with larger quantum codes, and we construct them in a moment.
I'm not sure if I understood this visualization. So first on the left upper half, does this correspond to like x4, tensor x5, tensor x6, tensor x7, or what?
Yeah, so the qubit labels you have written next to it. And so yeah, so this is this is exactly what it is. So this is x4, tensor x5, tensor x6, tensor x7. Yes. That's what it, it didn't occur to me that, yeah, that's exactly what it means. So this is a graphical notation of tensor products.
And why do we have 7 qubits now?
Why do we have 7 qubits now? Because it's a good choice. So the task that stands. So overall, we are looking to find good quantum error correction codes. We had a code that was of pedagogical value, but it failed. And this was our 3-qubit repetition code. It failed because it could not correct local Z errors. So our task, therefore, is to find a decent quantum code, and that corrects both. That corrects Z errors and X errors. And the Steen code was one of the first such codes found. Later, a smaller code with 5 qubits was found, but the Steen code is still the simpler one. So yeah, it is a relatively simple quantum error correction code that does the job. I mean, it does satisfy the minimal requirements of correcting one local error. Good. Okay, so here we go. That's our Steen code. Yeah, it's quite widely used. Where is it used, actually? It is used in the proof of the threshold theorem. So I think we saw that back on the previous slide. Yeah, I mean, we're not going to prove the threshold theorem here, but the formal proofs of the threshold theorem, at least the ones I know, are based on the Steen code. Okay, so it has a meaning. It has a meaning in quantum error correction theory. Okay, threshold behavior. Yeah, so we want to make that curve steeper. And what we have seen so far is, well, yes, so if no error occurs, that's fine. If a single error occurs, that's fine too. We can correct that. If 2 errors occur, the code will fail. And so if you do the combinatorics in a sloppy way, but let's not get into the details, there's 21 combinations of local errors. I mean, 2 error combinations that lead to failure. So that's why is the 21 here. This is an event that occurs to order p squared, and we forget about the corrections. I mean, there is a 1 minus p to the 5, but never mind. Yeah, let's just go with the leading order. So this is how, for small values of p, the logical error depends on the physical error. Okay, so so far we are only getting error suppression. Okay, but now we we want to improve upon that. And what we do is we introduce a procedure called code concatenation. So we take a qubit, encode it. I mean, it's 3 here, but that's just a matter of drawing. Imagine this would be 7 for the Steen code. And then we don't stop, but we encode again. We take every one of these qubits and encode it again, and again, and again, and again. And this gives us a concatenated code. Yeah, I mean, it's going to be a very large beast very quickly. Okay, and so then when you have this very large beast, you begin operating it and begin correcting error. So you would begin at the lowest level. Maybe in the drawing, the lowest level is here, so you would do error correction at that level. And with a certain probability, 21 p squared, with p the physical error probability, this will result in a logical error. Okay, so you get a logical error probability here. So you are making your next error correction procedure on the next higher level. And again, this results in an error probability up here. And you do error correction one last time and get back to the top level. And so the question is, what happens to the physical error probability when you go those various layers, when you go through these various layers? And that is the formula given here. So if this PL is the error probability at a certain layer, PL plus 1 is the error probability one level higher up. And it's going to, if P is already small, it's going to be smaller. Okay? And so graphically, it looks like this. So if you are, so again, there's this intersection point. So this curve is 21 p squared. And so, yeah, so you have an intersection point at 1 over 21. If you are below, then this recursion leads you to smaller and smaller values. So if you do this code concatenation arbitrarily often, and you start with the error probability below the threshold, you run into this attractive fixed point. So you will be very close to 0 after sufficiently many iterations. Yeah? After sufficiently many iterations of encoding, concatenations of encoding. However, if you are above the error threshold, well then this successive encoding only makes it worse. Okay, so you better be below the threshold, and then you can, if you make your code large enough, if you concatenate sufficiently often, you can make your error arbitrarily small. Yeah, so that's an important point. Are there any questions about this?
Is this Steen code somehow be proven as optimal or something like that? So,
No, it's not optimal. Not optimal. I mean, the question is, what is optimal? I mean,
it's proven that there are no less than 7 qubits to cover 1 qubit.
Yes. Okay. So yeah. So there are these bounds, these trade-offs between rate and what's called distance. A code distance. Let's say it in, we haven't introduced the term distance yet. So let's just say there are trade-offs in the number of physical qubits you use for encoding and the number of logical qubits you have and the number of errors you can correct. Yeah? So given, given, say, the number of physical qubits is fixed, then there's a trade-off. Do I want to encode more qubits, or do I want to suppress errors of higher weight? I mean, 1 local, 2 local, 3 local. So there's a trade-off, and a bound is known, and the Steen code is not optimal with respect to this bound. Yeah, so it's not optimal. So we have a 5-qubit code. It's probably optimal that does the same thing. But the question is this really the right notion of optimality for computation? And there is others other considerations that come in that I'm kind of racing towards. So I hope we will get there. Okay, good. So about this concept of code concatenation and the fact that there is an attractive fixed point here at logical error probability 0, has that become clear? So this is how we overcome our earlier finding that the code only suppressed the error but not eliminated it. So with code concatenation, we see that we can suppress an error arbitrarily to an arbitrary degree. It's just a matter of resource spending. Yeah? How large must I make my code to suppress an error to a certain degree? Yeah? Okay, so now comes an exercise that I will not have time for. But I think it's beneficial for you if you do it. So I think maybe I put it on the homework assignment. So the first question is now, for this recursion relation, what's the error threshold? Yeah, we answered that already. It's 1/21. But the question is now, below threshold, how is the error suppressed with the encoding level? And more importantly, how is the error suppressed with the code size? Because as you go through this concatenation, the code becomes exponentially bigger. The size of the code is exponential in the concatenation level. And so that maybe kind of rings a bell. You think maybe this procedure is super inefficient, but it is not. It's a bit inefficient, but not super inefficient. So, and the reason is that the suppression of error is faster than exponential in the coding level. And so if you work it out, the code size you need to spend is only polylogarithmic in 1 over the error you want to achieve. And I think that's a useful exercise doing. I make sure it is on the next problem sheet. Unfortunately, we don't have the time right now, but it's a good exercise to make. So far, okay. Let's just kind of recap what we did. Okay, we have figured out the basis of quantum error correction. We have understood threshold behavior. We have ignored a lot. We have ignored the fact that the error correction procedure itself, I mean, it's physical operations that also introduces error. We just said, okay, we measure these operators and that presumably can be done perfectly, but it can't. So we had, in a more careful analysis, we would have to think about the errors that are introduced when figuring out the errors. These we would need to take into account. We have no time for that, but a serious analysis must do that. And we have only been talking about memory so far. We have not been talking about computation. And that's what we want to talk about. And that can be fixed. That we don't want to talk about here. Okay. So the puzzle. Any ideas about the puzzle? What was wrong with this argument about drift? Okay, I'm not going to resolve it here. So you can think about it more. Okay, so 2 more things. One will come up a little later down the road. That's the Kitaev surface code, and I want to be super brief. So this will come up when we discuss the fault tolerance of measurement-based quantum computation. Okay, so this is another stabilizer code that is kind of popular. I mean, fairly popular, I would say, very popular maybe. And this is what it is. So it is a qubit that is arranged on it's a code that's arranged on a grid. So you have a simple 2-dimensional grid, and the qubits are located on the edges. And what else do we need for a stabilizer code? We need the stabilizer generators. And here you have them. So it's tensor products, yeah? So when I'm drawing this, it means tensor product. So it's a 4-fold tensor product of sigma z's. That's a stabilizer. And then likewise, you have a 4-fold tensor product of Pauli spin flips x arranged around a site. That's also a stabilizer, and you have these stabilizers for every plaquette and every site. And they commute as they are supposed to. And they give you for the boundary conditions shown here, they give you one encoded qubit, and these are the encoded Pauli operators. Okay, I don't want to talk more about it. That thing is called the Kitaev surface code. Yeah, so why is it relevant? It goes nicely with quantum computer architecture, particularly, I mean, Josephson junction, superconducting devices, these type of things, because what's good about it, that these operators, they are confined to a small region. So those you'll have to measure, and you have to figure out how to do that. And you find that there is circuits only composed of local measurements and short-range entangling gates that do that for you, that allow you to measure these operators. And short-range entangling gates is something that you can easily do with superconducting qubits. It would be very hard to provide for long-range gates in that physical architecture. Here you don't need it, and that makes the code quite popular. And if you look at the Google device or the IBM device, I mean, the Google device is exactly geared towards running that code, and the IBM device is geared towards running similar codes. They use all these topological quantum codes, and what makes them topological we can also discuss some other time. Okay, so that's the surface code, that's the code to remember. For practical purposes, it is much more relevant than the Steen code. Steen code is used in the proof of the threshold theorem, but anybody who wants to make a fault-tolerant quantum computer would not consider the Steen code. Probably would start out with a surface code and then move on to more complicated codes. But that's all I'm going to say about it. So please don't forget about it. It's a fairly important quantum code. But I want to talk about something else. I want to talk about computation on encoded qubits. Good. And so there is the problem of error propagation. And so what is that? So suppose this CNOT here would be part of doing some encoded gate. So the overall procedure would be, okay, so we're doing a bunch of gates, and that makes our encoded gate, and then we do an error correction, and then we just start over with the whole thing. So it'd always be encoded gate, error correction, that just kind of filtering out the errors, next gate, next error correction. So that would be the plan. Okay, and so here is, if your encoded gate operation contains a CNOT like this can give you trouble. And I want to explain to you why. So, and we have dealt with these propagation relations of the CNOT before. So you remember? So an error occurring before the CNOT is the same as CNOT occurring first, and then a correlated error. Yeah, so you have calculated that. Okay, and so now that's now happening before the error correction. Suppose it's all errors there are, but this is now a two local error. If this is a small quantum code, it will fail. Yeah, the quantum code is not designed for two local errors if it is a small quantum code. So we have a single event, an order P event, that ruined the error correction. And what made it happen was this propagation effect. We had an entangling gate in our encoded gate procedure that kind of arranged for one local errors to ruin the error correction. Okay, so that's not a good way to do an encoded gate. Yeah? And this observation leads us to transversal gate operation. So this is how you want to do encoded gates. Yeah? So you want no interaction. So you want in order to do some encoded gate, you want to act on qubit 1 individually and qubit 2 individually, and all the subsequent ones just individually, no interaction. And well, if you can do it like that, well, then these propagation effects that we saw on the previous slide, they cannot occur, because an error that occurs here always stays here. It does not jump to the other qubits. So that's how you want to do it. But the question is, can you? It's easy to see that if unitaries V are very close to the identity, then what this gives you is an error. Yeah? And that's not supposed to be an encoded gate. So there must be constraints. Yeah? And so the question is, for what encoded gates can you do a transversal construction? Good. So that's our question now. Are there any questions here at this point? Not the case. Okay, then let me move on. Okay, so now, good old Steen code, we can show that the Hadamard can be done transversally in the Steen code. Yeah? So the Hadamard gate done 7 times with the encoded Hadamard. So transversal gates do exist. Okay, so let's see. This is in fact a checkup. Okay, I'm not sure we have the time for that for you to do now, but how would you do it? How would you approach that problem? I mean, how would you prove what I just stated? Yeah, that the Hadamard is transversal for the Steen code.
The sheet there does not propagate twice.
Yeah, okay, so so that was a motivation for doing transversal gates. So the propagation is good, but even in the absence of errors, it has to do the gate. Why does the Steen code do the Hadamard transversally? Yes?
I would probably start by figuring out the state which the Steen code stabilizes, and then calculate both effects, so the effects on all the qubits.
But it's not only a single state, it's an entire space.
But can't you do it in analogy to what we did earlier with the repetition code? So just take the granular state in the stabilized space, then apply the gate, like commute through to the individual qubits.
Commute through the individual qubits? Can you say that again?
So, I mean, you only asked how we would approach the problem. I don't know if there are any problems popping up if I try this.
Yeah, no, I mean, certainly not. But you know, you are a physicist. Are you a physicist? If you are a physicist, you never want to work hard. So you wanna find a way to do this efficiently. And so maybe, okay, so you wanna know, so you wanna know what that state looks like. And so, so this state is now, can be stabilizer state, need not be, it is from a stabilizer code. And we remember when we have an evolution like that, we know what happens to the stabilizers. Yeah, so the stabilizers undergo the same transformation, but under conjugation. And there must be space for a dagger here somewhere. Okay, so that's what's going to happen to the stabilizers. And then the same is also going to happen to the encoded Pauli operators. And so what you can verify for yourself if you want to spend the time is that a Steen code stabilizer under the Hadamard conjugated will remain a Steen code stabilizer. Not the same one, but a stabilizer. So maybe let's go back to the Steen code stabilizer. Yeah, here we go. So under the 7-fold Hadamard conjugating, this stabilizer will become that. Yeah, X is conjugated into Z. This will become that. They'll just switch. And the same is going to happen here. They will just switch. They will just switch. So the stabilizer is not mapped onto itself element-wise, but it is mapped onto itself as a group. Yeah, the group remains the same. Group generated by these 6 stabilizers. Yeah, so it remains a state with the same code stabilizer. Yeah? So the code space is preserved. Yeah? So that makes the Hadamard a transversal gate. 7-fold Hadamard transversal gate. We just need to figure out which transversal gate it is. And that we see when we look at the encoded Pauli operators under conjugation. Yeah, same thing happens. You know, if 7-fold Hadamard, they are interchanged. 7-fold X becomes 7-fold Z and the other way around. And that's exactly what's going to happen under Hadamard. So this is the encoded Hadamard. Okay, so that's basically the argument. And now if you can see if that's sunk in, and you can do this argument one more time for yourself. Let me just say, the gate, you remember the gate S that we discussed in the last lecture. So this is e to the minus I pi over 4z. Yeah? So pi over 2 rotation about the z-axis. That gate is also transversal for the Steen code. Yeah? Now that you've seen it for the Hadamard, maybe you can show that. Okay, so last point for today's lecture. So I want to introduce another quantum code, and it's from the family of Reed-Muller codes, which the Steen code is too. Anyway, so I mean, some of you may have seen a cube in those arrangement of 7 qubits that I saw earlier, and now we are bringing this cube back. Okay, so here is the 7-qubit Steen code. So this is the missing, so the qubit missing from the cube. There's a coding theory name for that thing missing. It's called a puncture, but never mind for now. Okay, so we have this remainder of the cube with this one vertex missing, and here you see a stabilizer associated with one of the phases present. Okay, and so we now draw a similar structure to the extent we can, one dimension higher up. So this is now a 4-dimensional hypercube. And again, it has one vertex missing, but otherwise is the same. So now going out from this missing side here, there were 3 faces in 3 different spatial directions. Now there's 4 different spatial directions here, and there's now 4 cubes opposite to this single vertex. Okay, so these codes are siblings. So they come from so-called Reed-Muller codes. I don't want to go too deeply into them. So there is, the Reed-Muller codes come with 2 parameters. One measures size. So the 3 means that you have 2 to the 3 minus 1 bits here, or qubits, 7. The 4, here's a 4, you can't see it. This is Reed-Muller 4, 1. So this means that there is 2 to the 4 minus 1 equals 15 qubits in this arrangement. And the second parameter is for the structure, but I don't want to talk about that right now. Okay, so these are very similar codes. This one is a little bit bigger. I mean, essentially twice as big. And now let's talk about the stabilizer of this code. So we have, for both X and Z type of stabilizer, we have stabilizers associated with the volumes in this hypercube. So like up here and to the right and to the back and so on and so forth. So there's 4 of them, both for X and Z. And then we have additional Z-type stabilizers for intersections of these cubes. So say this cube here to the left and this cube at the top, they intersect in this face, for example. Oh, sorry, I've shown it otherwise. So this cube here on the left and this cube in the back, they intersect in this face here to the very left, and there is a 4-fold tensor product of sigma z stabilizer associated with that face. And so there's 4 such cubes. They pairwise intersect, and so this gives us 6 more elements of the Z-type stabilizer. So we have altogether 4 plus 4 plus 6 makes 14 stabilizer generators. This is exactly good enough to encode 1 qubit in a 15-qubit code. Okay, so this is the Reed-Muller code in kind of a geometrical display. Why is it important? And that's really the strange thing. So this has an interesting transversal gate. So there's the T gate. So the T gate is e to the minus I pi over 8 z. So remember, the gate S of last time was e to the minus I pi over 4 z. So T is the square root of S. So S is transversal for the Steen code, but T is transversal for the Reed-Muller code. And so remember, oh yeah, we've seen this T before. So T is a non-Clifford gate, and it is part of a universal set. So you need something like that to compute, and you need a fault-tolerant version of that to compute fault-tolerantly. Yeah, and the Reed-Muller code gives you that. It's kind of rare among stabilizer codes that they give you transversal non-Clifford gates. I mean, I think from the Goddard-Monod theorem, you know by now that Clifford gates and stabilizer states and stabilizer codes, this is kind of a package that fits together. But here we have something outside this package, a non-Clifford gate, and it can still be done transversally for a stabilizer code, namely for this Reed-Muller code. Okay, so and that property makes this 15-qubit Reed-Muller code a very important code. And as we will see next time, so next time we start with this course proper. So this was all preparation. Next time we talk about quantum computation with magic states. And this scheme, quantum computation of magic states, makes a living out of this property. Yeah. So that property is going to be very important for that computational model, which is why I reviewed it here. So that's all for today. And yeah, so quantum computation with magic states coming up next Monday.